Hello, everybody, and welcome back. I hope you're all doing well. Root Beer here. We're looking at question 3 on our 2012 Euclid paper. So A part, a 200-gram solution consists of water and salt. 25% of the total mass of the solution is salt. So 25% of the 200 grams is salt. How many grams of water need to be added in order to change the solution so that it is 10% salt? Okay. Well, we need to figure out how many grams of water, so let's give a name to that. So let W be water to add, and if we care about this, it's in grams. Okay. Now, we can work out how much salt there is, because it's 25% of 200 grams, right? So that would be 25% over 100%, or you could just say a quarter of 200. Okay. That'll be 50 grams. So 50 grams of salt. Okay. And if we care about it, then that means that there's 150 grams of water currently. Okay. I don't really care how much water there is right now, because what we're going to do is we're just going to add the water. Okay. Now we want the amount of salt. So we do our work, and we want 50 grams, which is the amount of salt. Now we want this to be 10% after we've added the water. So we had 200 grams, and then we're adding some amount of water, right? So this gives us a nice equation. 50 is 10% of 100 plus W. Now, you might be able to do this in your head and say, okay, 50 is 10% of 500, so we should be adding W equals 300. But if not, okay, you're not gonna, if you can't make that sort of a connection, or you just don't think to make that sort of a connection, that's okay. We can see that 50 grams is 1/10 200 plus W multiplied by 10. We see that 500 is 200 plus W. From there, it's very quick to see, I need 300 grams. Okay. So if I had 300 grams of water, the salt content will go from 25% down to 10%. Okay. No salt is added or lost. We just have more water, and it shifts the ratio. So that's our light bulb question. We just need to put 300 in to the box provided, and we're done. Now we're on to B part. The correct formula for converting a Celsius temperature to a Fahrenheit temperature is the Fahrenheit is 9/5 of the Celsius plus 32. This is true, actually. And you'll notice something cool happens. If it's minus 40 degrees Celsius, it's also minus 40 degrees Fahrenheit. These are the only two times the temperatures, or this is the only time you can just say it's minus 40 out. You don't have to specify the temperature scale. Okay. Anyway, to approximate the Fahrenheit temperature, Gordy doubles C and adds 30 to get F. I can see why he's doing that. 9 is almost 10. 10 over 5 would be 2. And 32, well, why not just add 30? So this gives us a new calculation, F, 2C plus 30. Now, if F is less than the actual Fahrenheit, the area in the approximation is F minus F. Otherwise, the area is F. So we just take the bigger one and subtract the smaller one, whatever they happen to be. Okay? Determine the largest possible error in the approximation that Gordy would make when converting Celsius with C, converting Celsius when your C value is between minus 20 and 35. Okay. So where's the biggest error going to be? Well, is there a way to tell which one's going to be bigger, F or F? Well, so here let's work on two cases. Suppose that the actual value of the Fahrenheit is bigger than F. Then our error is F minus F, and that's 9/5 C plus 32 minus 2C plus 30. Okay? Well, that's 9/5 C plus 32 minus 10/5 C, just so I can easily calculate. And then minus a plus becomes minus 30. So we get 2 minus 1/5 C. Okay? This only works if this is bigger than 0. Okay? We should probably note that off to the side, you know. So we have f greater than f implies f minus f is greater than 0, right? Because that's the case we're looking at. Okay? So this expression here must be greater than 0. Now, how do I make this as big as possible? I make this as big as possible by subtracting off the smallest thing, or the largest negative thing. Okay? But we don't really have to do that. We can just say 20. C is between minus 20 and 35. So a fifth C is going to be between minus 4 and 7. And now if I multiply that by negative 1, the signs flip around, and this is an important thing to keep track of. Okay? And now if we add 2 to both sides, okay, we'll get our expression. Okay? Now the biggest this error can be then is 6. And that happens when C is minus 20. So since f is greater than f, my error is greater than 0, so we get so the biggest this happens, biggest error in this case is 6, and we can see that occurs when C is minus 20. Okay, but is that the biggest error possible in this range? Okay. Now let's do the other case. Suppose that we've got a smaller f than our approximation, right? Okay. What does that mean? Well, then we're going to use f minus f as our error. Little f minus capital F is our error. So that'll be 2c plus 30 minus 9/5 c plus 32. And it's really just the flip of the equation. It absolutely is. So it's just 1/2 c minus 2. Okay? But again, this expression here is going to have to be bigger than 0. Okay? So our c value is in this range. As we already saw, a fifth c is in this range. And then if we subtract 2, we get this. So this error is biggest when C is 35. Okay? That's where the error is biggest. So, but 5 is less than 6. 6 is greater than 5. What did we want? Did we want the C value? Determine the largest possible error. So 6 is still the largest possible error. Okay. Now you might notice the equations here were kind of similar and the inequalities that you're getting were kind of similar. One way you could have done this is just said, well, let's look at the absolute value expression. Okay. So the error is going to be biggest when this expression is biggest, and then we could have taken a look at this and said, well, it's biggest when 6, regardless, like, you know, it could be minus 5, but absolute value of minus 5 is 5, and that's still less than 6. And this would have avoided case-based work. It's a little quicker, I would say, but it's not like we really had a problem doing these two different cases here. It's a little faster, but you'd have to make a note. Why does this work? Either we use f minus f or f minus f, and it all depends on which one's bigger. And so that means, you know, this expression's got to be positive, or this expression's positive, well, that would make this expression here negative, and you have to justify why this counts. I wouldn't say it takes too long, but it's probably worth at least a mark if you wanted to go that way. Okay, but it's a little faster, but not particularly faster. So that finishes up question number 3. We did part B quite nicely, and we can move on to question number 4, and we'll take a look at that next time. Until then, take care, have a wonderful day, and I'll see you for more math in the future.